Okay, we're going to start this third video in the sequence by doing a little peer review. We've got three people looking at a situation, and Ben there says that the force of normal should be 50 newtons. Dunn that says it should be 75, and Warren P says it should be 100 newtons. So they each have an idea. Only one of them can be correct, so we have to figure out which one that is. I'll start by doing what I need to do whenever there is an uncooperative force. So the 50 newtons at an angle of 30 degrees is an uncooperative force. So what I have to do is figure out how much of that force points in the horizontal and how much of it points in the vertical. So I'm going to break it down into a horizontal component, and I'm going to use the cosine of 30 degrees, and I'm going to multiply that by the force of 50 newtons, and that's 43 newtons in the x direction. That's supposed to be an x. And then the vertical direction here, I'm going to use the sine of 30 degrees, which is 1/2. And 1/2 of 50 is 25. So 25, and that's newtons, and that's newtons. That's Fy. Okay, now let's just look in the vertical plane and we can figure out who's going to be right. It's across a horizontal surface, so we would expect the object not to accelerate upward or downward in this situation. So I need the normal force, all the vertical forces, so I need the normal force, the upward Fy, vertical force, and the gravitational force to all add up to 0. So the normal force plus 25 must equal 100. That would indicate that the best answer should be 75 newtons. Now let's just go back and quick check the other two and see if we can make sure that they are not right. Now if it had been 100 newtons, that would be the easiest thing to say. But in that case, the normal force wouldn't be removing or helping to lift off at all. The 25 newtons wouldn't be taken into account. Keep in mind when I did do that cooperation, that get that uncooperative force out of there, it's no longer there. It's just the vertical and the horizontal force. So it couldn't be that. That's the simplest if there are no other forces acting on the object, and if the surface is horizontal. That's not it. 50 wouldn't be enough. We'd have 100, and then we'd have 50 plus 25, so we'd have too much downward, and our object would accelerate downward. So it has to be a balance. So it has to be done, so he's got the correct normal force of 75 in this particular case. Okay, so we'll try to apply all those ideas and fill in the blanks in these different situations. Again, the first thing I'm going to do is I'm going to remove this applied force and replace it with a horizontal force and a vertical force. To find the horizontal force, I'm going to take the cosine of 29 degrees, and I'm going to multiply that by the force that's applied in that direction of 38 newtons. And I'm going to round that to two figures, so that's 33 newtons this way, and that's Fx. And then the Fy is going to be the cosine, the sine, that's on the opposite side of the triangle, of 29 degrees. And we're going to multiply that by the 38 newtons as well. So that's 18.4. That's going to round to 18 newtons. Now again, once that's happened, I'm going to get rid of this force entirely. It's gone. I've replaced it with a horizontal and a vertical component that add up to make it. Now the object's gravity, it's 3 kilograms. If we're using 9.8, then that's going to be 3 times 9.8, which is going to be 29.4 newtons, which will just round off to 29 newtons for two significant figures. Now, if there hadn't been an applied force, our normal force would be 29 newtons. But because of the addition of the normal force, then we have to have the normal force, which is vertical, up, and the vertical component that we found, the 18 newtons, also up. They have to add up to 29. So 29 minus 18 is going to leave us 11 newtons for the normal. So the vertical force again was 18 newtons. That's going to add to 11. That's going to make 29. Again, in terms of trying to find the acceleration or net force, all of those are going to end up canceling each other out because of the level surface. Now I have 33 newtons to the right. So when I look for the net force, which means the summation or add all the forces, if I call it to the right positive, to the left negative as I have been, then I'm going to have 33 newtons plus a negative 5.5 newtons. So 27.5 newtons. That's an N. For the net force. Now again, that really rounds off to 28 newtons to two significant figures. And then the acceleration is going to be the 28 newtons divided by the 3 kilograms. So to find the acceleration, you're going to take the net force and you're going to divide by the mass. 28 divided by 3, a little bit more than 9. And 9 1/3, so 9.3 is two significant figures. And again, both of those are going to be to the right. So positive would also work. If we're doing that for this next one, in number 5, this time the mass is larger, so we need 4 times 9.8 to be our weight of the object, which is 39.2. Again, that rounds to 39, just about 10 times larger. Because I'm only using two significant figures, if I use 10 newtons per kilogram, I'd probably be just as well off in this case as any other. Now I also have to, again, figure out the fx. Again, that's going to be the cosine of 38 degrees. And I'm going to multiply that by 55 as the overall force. I'm going to round that off to two significant figures, and I have 43 newtons. I also have to figure out the vertical force. Okay, this time I'm drawing in a slightly different location than I did last time. You just need to realize it's going to be coming out of that center. It's going to be going vertical. Now I'm going to use the sine of 38 degrees this time, and I'm going to multiply that by 55 and round it off, and I get 34 newtons. Now again, for our purposes, the gravitational force and the normal force are going to cancel out. So and the vertical forces are going to cancel out. So the normal plus the vertical here, 34 plus normal, has to equal 39. That makes this 5. But when we're going for the acceleration again, that's going to cancel out with the vertical gravitational force. What we're really interested in is the 43 newtons and the 4.5 newtons. So our summation of forces is going to be 43 positive plus a negative 4.5. Gives us 38.9, which rounds off to 39 newtons. Now, in this case, it's just a coincidence that it happened to be the same as the weight. Sometimes those situations will occur. Then to find the acceleration, we're just going to take the 39 newtons, and we're going to divide that by the mass of this particular object, which is 4. And we're going to round that off to two significant figures, and we get 9.8. Notice that the net overall force being the same as the weight, we end up with an acceleration that is the same as the acceleration due to gravity. Now, if it had been the acceleration due to gravity causing the motion, the object would be accelerating downward. In this case, it's accelerating to the right. There are situations when you are pushed or pulled by forces that create accelerations that are equal to the acceleration due to gravity. We call that 1g. When you go into situations where you get accelerations greater than 1g, we say you are undergoing positive g's. In other situations, like at the top of a roller coaster, you might feel like you weigh less. or if an elevator is slowing down as you're coming up to a floor. So we call those negative g's. So we can relate all our accelerations back to the acceleration due to gravity and have some kind of basis to compare how much they are. Okay, so we got one more to go, so let's go ahead and finish that one off. The big one about this one is we're being pulled at constant speed, so we're going to have to figure out the friction. Now, the value of the constant speed is not what's important. What's important is to be at constant speed in a straight line, all the forces have to be balanced. So our net force is going to have to come out to be 0. Again, the same thing I'm going to do the last time. I'm going to take this force and I'm going to break it down into its vertical and horizontal components, and then I'm going to get rid of that force. So 80 times the cosine of 45 is going to give me 57 newtons. Now, with it being 45 degrees, then I know Fy is the same. These two legs are going to be the same at 45 degrees, so that's 57 newtons. Now again, that one's gone. Let's get rid of it. Now the vertical forces and the horizontal forces are going to have to cancel out. Our mass is 20, so 20 times 9.8 is 196. And I related two significant figures. That's really going to be 200 newtons, so we'll go with that. The 200 is going to have to be balanced by 57 plus whatever the normal force is. So if I take 200 and subtract away the 57 that I have already, then I'll be at 143 newtons. Now I need a balance, so if I'm pulling to the right of 57 newtons, I must have a frictional force pulling against me of 57 newtons. Now the object is in translational equilibrium. It's still moving, but it's not moving because of any applied forces. It's moving because once it's inertia, once it's in motion, its inertia will keep it in motion. All we have here is a force balance. We're not accelerating the object, we're keeping it at a constant speed in a straight line. So that's a good case of a good example of translational equilibrium. Okay, in our next series we'll be looking at what happens when the surface is inclined and how to deal with that situation.